Hello everyone. In this video, we discuss the nature of singularities of the following functions. Here we have 8 functions, 8 complex functions. We need to find the singularity and its nature. So let's start with the sin z by z. Okay, first function sin z by z. So we have the denominator equal to 0 for z is equal to 0. That is 0 is the singularity of the function. We need to find the natures. Z equal to 0 is singularity. We need to find the nature of the function. We have 3 singularities. We have isolated and non-isolated singularity. In isolated singularities, we have removable, pole, and essential singularity. I discussed these 3 singularities in my previous videos. So here we need to find z equal to 0 with the nature of z equal to 0 in this function sin z by z. So here I use Lorentz series expansion of this function sin z divided by z. So 1 by z, we have the expansion of sin z as z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 by 7 factorial etc. plus etc. This is the expansion of sin z and 1 by z here. So multiply 1 by z throughout. So this is 1 minus z square by 3 factorial plus z raised to 4 by 5 factorial and minus z raised to 6 by 7 factorial plus etc. So here the Lorentz series expansion of sin z by z doesn't have any negative powers of z. The term containing negative powers of z. That means in Lorentz series expansion, I already discussed these theories in my previous videos. Lorentz series expansion an z minus z naught all power n minus infinity to infinity. If this series expansion doesn't contain any negative terms, that means a minus n is equal to 0 for all n, then the singularity is removable. If this term contains a minus n is not equal to 0 for n is equal to m and for n greater than m, a minus n is equal to 0, then this is called pole of order m. That means if we have the powers of negative powers of z in terms, if we have 1 by z, negative power of z, that means z raised to minus 1 is 1 by z, and 1 by z square, 1 by z cube in Lorentz series expansion of some particular function. That means here we have 3 terms and all other 1 by z cube, all other terms are z raised to 4, all other terms are 0. All the coefficients of other terms are 0. Then this series here we have positive terms. That means z, some a1z square, a2z square, a1z etc. And the only negative power is till the cubic power z cube. Then we have pole of order 3. So that is the concept. So in this case, we don't have negative powers, and if it is essential, then we have a minus n not equal to 0 for infinitely many n. This is the third case. For infinitely many n, we have negative powers of z, the term containing negative powers of z, infinite terms. then it is essential singularity. So that is a concept. So here we have only the positive powers of Z, no negative powers of Z. That means this is Z raised to 0, Z square, Z raised to 4, only the positive powers of Z, no negative powers of Z. That means the singularity Z equal to 0 is removable. So, the nature of the singularity Z equal to 0 for this function is removable singularity. Now, our next function is cos Z by Z. Same way, we can use the Lorentz series expansion of cos Z by Z. So, cos Z divided by Z. Here also Z equal to 0 is the singularity of this function. Okay. Now, we need to find the series expansion of cos Z by Z. So, 1 by Z outside. Expansion of cos Z is 1 minus Z square by 2 factorial plus Z raised to 4 by 4 factorial minus Z raised to 6 by 6 factorial, etc. So, multiplying with 1 by Z, we have 1 by Z minus Z by 2 factorial plus Z cube by 4 factorial, etc. So, in the series expansion, these terms all are positive powers of Z. So, this is the only negative power of Z, the term containing negative power of Z. So, the term containing negative power of Z is only the one term. That means, this is Z equal to 0 is pole of order 1 or simple pole. So, Z equal to 0 is a simple pole of cos Z by Z. Means Lorentz series expansion only contain the first power or negative power Z raised to minus 1. This is the only negative term. So, this is pole of order 1. Okay. Now, third question. Sin Z by Z square. Same way we can use sin Z by Z square. That means, here I can write sin Z by Z square. If it is Z square, this is 1 by Z square and this is 1 by Z and second term is Z by 3 factorial and third term is Z cube by 5 factorial and this is Z raised to 5 by 7 factorial. That means we divided each term with Z square. So, here we have 1 by Z. That means 1 by Z is the only negative term, negative power of Z. That means Z equal to 0 for sin Z by Z square. Sin Z by Z square, Z equal to 0 is pole of order 1. That means simple pole. Okay. Sin Z by Z as Z equal to 0 removable singularity. Sin Z by Z square, Z equal to 0 is simple pole. Clear? Now, the fourth function, e raised to Z minus 1 by Z. Now, let's expand the series. E raised to Z minus 1 divided by Z. So, we know that 1 by Z outside, e raised to Z. E raised to Z is 1 plus Z square by 2 factorial. Z cube by 3 factorial plus etc. minus 1. There is a minus 1 here. So, 1 minus 1 cancelled. Divided it with Z. First term is 1 plus Z by 2 factorial plus Z square by 3 factorial plus etc. Here all the term are positive powers of z. No negative powers, no term with the negative powers of z. So, here the singularity is z equal to 0. Clearly the z equal to 0. Denominator is 0 when z equal to 0. Z equal to 0 is the singularity and it is removable. Okay. Since a Lorentz series expansion doesn't contain any term containing negative powers of z. So, z equal to 0 is removable singularity. Now, fifth function, log 1 plus z divided by z square. So, let's expand log 1 plus z divided by z square. So, expansion of log 1 plus z is 1 by z square outside. Log 1 plus z is z minus z square by 2 plus z cube by 3 minus z raised to 4 by 4 plus z raised to 5 by 5, etc. So, divided by z square, 1 by z minus 1 by 2 plus z by 3 minus z square by 4 plus z cube by 5, etc. So, this is the only term containing negative power of z. All other are non-negative powers. So, that means here the singularity is z equal to 0 and z equal to 0 is simple pole. Z equal to 0 is simple pole. That means pole of order 1. Now, sixth function is e raised to 1 by z. Okay. Let's expand the function e raised to 1 by z. The expansion is 1 plus, instead of z we have 1 by z plus z square 1 by z square divided by 2 factorial plus z cube by 3 factorial. That means 1 by z cube by 3 factorial, etc. Now this is 1 plus 1 by z plus 1 by z square 2 factorial plus 1 by z cube 3 factorial plus etc. So, okay, this is our series, and this is the series of e raised to 1 by z with infinitely many terms containing negative powers of z. 1 by z, 1 by z square, 1 by z cube, the next term is 1 by z raised to 4, etc. So, here we have infinitely many negative terms. So, infinitely many negative powers of z or terms containing negative powers of z means the singularity is z equal to 0. That means e raised to 1 by 0 infinity, it does not exist. That means z equal to 0 is essential singularity. So, it is not defined for z equal to 0. So, z equal to 0 is essential singularity of e raised to 1 by z. So, if we have infinitely many negative terms in Lorentz series expansion, then it is essential singularity. So, next is cos 1 by z divided by 1 by z. So, cos 1 by z divided by 1 by z. So, 1 by z we can write z. Okay, this is 1 by z. We can z. Okay. Now, cos 1 by z, expansion of cos 1 by z. Cos 1 by z expansion is 1 minus z square by 2 factorial. That means 1 by z all square by 2 factorial plus z raised to 4 by 4 factorial minus z raised to 6 by 6 factorial plus etc. So this is the expansion of cos 1 by z. Now multiply it with the z. It is z minus. This is 1 by z square 2 factorial. And multiplying it with the z means 1 by z 2 factorial plus 1 by, this is z cube for factorial, and minus 1 by z raised to 5 6 factorial, etc. So here this is the only positive power of z. All other are negative powers of z. So infinitely many negative power of z means z equal to 0 is the singularity of the function, and it is essential singularity. Okay. Here we have infinitely many terms containing negative powers of z. So z equal to 0 is essential singularity. Now the last question. Sine 1 by z. So let's check the singularity of this function. Sine 1 by z. Now let's expand sine 1 by z. Clearly z equal to 0 is the singularity of this function. So expand this function as z 1 by z minus 1 by z all cube by 3 factorial plus 1 by z all raised to 5 by 5 factorial minus etc. That is 1 by z minus 1 by z cube 3 factorial plus 1 by z raised to 5 factorial minus etc. That is, here also we have infinitely many negative terms containing negative powers of z. So z equal to 0 is essential singularity. Here also z equal to 0 is essential singularity. So all we did is we use the Lorentz series expansion of all these functions and find the nature of singularity, nature and behavior of the singularities of these functions. Hope you understand the solution. If you have any doubt, please comment below. Please subscribe and watch the video. Thank you.